Hi everyone, I'm Yi Tong. Today I'm going giving a critical review of a paper called Brain CNN, which present a AI system for automatic brain tumor grading using CNNs. And here's what I will cover. First, what problem the paper tries to solve, then the method used. Next, how the authors tested module and what they find. And finally, his and my critical comments on its strengths and weakness. The paper points out that brain tumor grading is hard and time confusing. Tau tumor vary a lot in size, shapes, and position, which makes measure grading subjective. So, the author suggests using AI to make the process faster and more consistent. In this study, the module built a CNN-based module called Brain CNN to classify MRI scan into WHO's grading. The module can process the scan within minutes and to capture small textual details that doctors may overlook. For the background, the paper you review the WHO grading system, which has four-level higher grading, means more aggressive tumors. The author used this system as the target labels for their classification task. The paper explained that grading affects treatment plan and the patient's outcome. Accuracy grades helps doctor choose the right therapy and evaluate survival rate. This gives strong motivation for their AI approach. The study applies module convolutional neural network to analyze MRI images before feeding data into the module. The author clean, unload, and normalize the scan. They focus on image features such as tumor age, brightness, and texture. And here is the workflow. According to the paper, the workflow has four main steps. First is collection MRI scans like T1, T2, failure, and then process and all the data. Then the third is predict the grade with CNN. Finally, visualize the output using color maps. The authors used 293 MRI cases, including both low and high-grade tumors. All cases were verified by PACE logic, which gives reliable ground truth. However, the dataset sizes are relatively small for deep learning. And for the right hand, for the data preparation, the paper describes several pre-processing steps such as standardization, denoising, and data augmentation. These are useful for module stability, but the paper doesn't mention any extra validation to test generalization. And for the module and the training, the module used multiple CNN layers with cross-entrapose loss and the Adam optimizer. Training include earlier stop and parameter tuning. However, the author don't compare their architecture with other CNN types, which limits the evaluation. For the right-hand optimization, the paper monitors loss and accuracy during training and adjusts learning rate and batch size. But it doesn't explain how Hydra maturators were chosen or whether they used any validation codes for tuning. And for the impact, the author claimed that Brand CNN can reduce doctors' workload and inter-observer disagreement. This is a valuable contribution, but the study doesn't include real-time user feedback or clinical trials. For the patient and society, the paper also highlights benefit for patients, faster diagnosis, and less waiting. There are good patient outcomes, petition outcomes through they remain hydropolitical since no patient data were directly tested. And for the result, the author report accuracy of 99.45%, which is very high. However, they don't provide details on cross-validation or class balance, so the number may be overfitting. Still, it shows the strong potential of CNN-based grading. For the practical application outcomes, the system could reduce the diagnosis time from hours to minutes. That's a clear advantage, especially in emergency situations. But again, without testing in real hospital, this remains a logical claim. For key result achievement, the paper proves CNN can achieve high accuracy for tumor grading. It also used transfer learning to improve performance on a small dataset. Yet, the lack of comparison with other modules weakened the claim of novelty. In the future, the author suggests use 3D CNNs and testing on other tumor types. They also plan to develop a lightweight version for mobile or remote use. They are good directions for practical deployment. For research direction, they also propose adding attention and the transformer layer to improve feature learning, and using edge computing to allow real-time predictions. They are promising but still conceptual. The paper calls for larger and more device dataset, and for combining MRI with other scans like PET-CT that would improve the generalization and the clinical usability. And for the getting involved, the author encouraged the hospitals and researchers to capitalize on the future trial. But there's no mention of open source data or code, which limits reproducibility. And for the final comment, to sum up, the paper presents a strong idea and a well organized CNN module. However, it lacks extra validation, comparison with other methods, and real-world testing. Still, it is a valuable step towards AI-assisted tumor grading. But in short, the paper shows a strong idea. Um, Still, it's a good step toward practical AI in medical imaging. Thank you for listening.